Good afternoon, gentlemen. Today we are going to be going over scientific measurements and metric conversions. This topic will be extremely important for you to understand to be successful in chemistry because this idea is going to follow us all the way through the entire year. So as you go through this, if there's anywhere that you're struggling, either make sure you find time to meet with me or make sure that you rewatch this video and have a really good understanding of this content. So starting off easy, we just need to focus on what is scientific notation. Whenever I talk about scientific notation, these are ways that I can write very large or very small numbers. So for example, the size of an atom is 1.0 times 10 to the negative 9 nanometers. That is an extremely small, that's, looking at 0.000000000 all the way to that. The other example is a mole, which is a quantity of 6.02 times 10 to the 23rd. Again, just like I said before, this is a really big number, so you're looking at 6.602 with 21 zeros after it. The three basic parts to a scientific notation number are as follows. You're going to see where you have the coefficient, and this will always be between 1 and 9.99. You will never see a coefficient that has like a 10 or a 0 point because we need to be between that. If you do see it, that means you did not slide the decimal all the way over. Then we have our base. In our case, our base is always going to be a times 10, and then based on that, we'll have our exponent that follows. If the exponent is a positive, kind of like the mole, for example, you're dealing with an extremely big number, so you'll have like the 602 and then however many zeros. If you're dealing with a negative, we're dealing with a really small number, so that's where we're going to get a 0.000, for example. Working with our calculator, you do need to feel confident in putting into scientific notation. What I mean by that is when you're looking at your calculator, depending on what you have, you don't want to use the multiplication operation. There are specific buttons that are on our calculator designed to put in our scientific notation. If we're working with a TI-30X2S, for example, this one we have a EE button, but it's as a button we need to access using our second or shift button. So if I was dealing with the TI-30X2S, I would have to type in my coefficient, so like 2.0. I would hit the second button, and then I'd hit my X negative 1, as that would give me my EE. Now, anytime you're dealing with this calculator, when you put in the EE function, so I just did like 2.0, it'll come up as a lowercase e. That represents my times 10, and then I would follow with my coefficient. So for example, if I had, an exponent. If I had an exponent of 2, I would have 2.0 second EE 2. If you're working with the TI-30XA, this one's a little bit different. You will type in your coefficient, and then because you have the EE button right here, you will hit that. But instead of giving an E like the TI-30X2S, it'll give it to you just like this up here. So you would get something that looks more like your coefficient with the exponent, but the calculator knows that when you hit that EE button that you're using the times 10. The other thing that I kind of want to point out is that when you're doing this, make sure you're utilizing the negative button. On the TI-30X2S, your negative is located under the 3. On the TI-30XA, your negative is also located, but it looks like a positive to negative switch, and that will appear in the corner. So let's practice together by putting in the scientific notation as a function. Again, because we have the times 10s, we are going to kind of separate those up because we are not going to utilize the multiplication. So there are my two coefficients with their base and their exponent. We're going to start off. So if we're dealing with the TI-30X2S, I will type in 3.4. I will hit my second EE. So remember, we'll do my 3.4 second EE. And because I have a negative 7, I'll type the negative button. I'll insert 7. Then because my function is a division, I will hit my divide button. And then I will continue with 6.3, second EE, 4. If you're dealing with the TI-30XA, I'm going to put it in like 3.4, EE -7. You can also just type the 7 negative, those will both work. And then I'll hit my divide, I'll do my 6.3 EE4 and hit my enter. When I do that, I should get a very long number. I'm going to simplify it down to 2 decimal places, so I may need to round up. So I'll do 5.4 times 10 to the -12. Now, your times 10 may come up differently. On the TI-30X2S, you'll get it right at the end. It'll be really small. And then if you're dealing with the TI-30XA, it'll be similar to your answer with the 7.3 with the exponent in the corner. So make sure you're always including that times 10. So try this calculation on your own. So remember, we're dealing with 2 scientific numbers. We want to use that EE. That is extremely important, especially when you get into doing these functions. So try this, answer the question on the side, and then we will continue on. Now, you might get this answer in 2 ways, but if we want to put it in scientific notation, I'll kind of walk through the steps. Oh, goodness. Okay, so I get 0.0126. I want to put this into scientific notation, so because I'm dealing with a small number, I will have a negative exponent. I go 1, 2 over to get 1.3 times 10 to -2. All right. Next is a little bit different. This is the one that we're going to be going over metric conversions. I'm specifically going to go over the sliding decimal method. And the reason that this is possible to do a sliding decimal method with this is because the metric system has a base of 10. So essentially each 0 is 1 decimal place. So I'm able to slide the decimal and I don't need to do any calculations. Looking specifically at the sliding decimal method, we utilize King Henry doesn't usually drink chocolate milk. The U or usually represents our unit. So if I'm working in meters, liters, grams, that is where the base will go. And the K represents kilo, the H represents hecto, the D represents deca, the D, lowercase d, represents deci, C represents centi, and M represents milli. So if we're looking at our first one where I start with 0.045 millimeters and I'm trying to get to centimeters, I need to figure out what direction am I going. So in this case, I'm starting with millimeters, so I have the milli, and I'm trying to get to centi. Because I am going up the ladder, this means that my number should get smaller because I'm starting with millimeters. So what I would end up doing is sliding my decimal 1 over to the left to get my answer. So I'll do that. And I will simplify by going 0.0045 centimeters. Now, the next one I have is 34.5 meters to kilometers. Similar thing, I'm going from meters to kilometers. So I'm going to slide 1, 2, 3 to the left, which this makes sense because the higher up you are, the bigger kind of your number is. So if I'm starting with a smaller unit to a bigger unit, then I should get something that has decimals. So I will slide this 1, 2, 3 to the left, and I will get 0.0345 kilometers. Now, the other way that you can solve using this method is by completing a factor conversion. Looking at the factor conversion method, the big difference between this and the sliding decimal method is that instead of sliding my decimal, I use fractions to convert between my units. This is also called dimensional analysis, or I will always refer to it as the train track method. This idea is extremely important because the factor conversions will come into play in later units, especially when you're not dealing with the metric system, where you may need to set up a train track. Now, when you are making the fraction, you always want to use the for every speech. Essentially, what this means is I ask with my base unit to figure out how many are in that unit. So for example, for every meter, there are 1,000 millimeters. This is helpful because it helps you build that fraction to show these relationships. Your prefix closer to the left will always get a 1. So for example, like I said, for every 1 meter, there are 1,000 millimeters. And the reason I can give the meter the 1 is because that's higher on the stair step. If I had for every kilometer, there are 10 hectometers, would be that other example. So for example, let's do this one together. Whatever I'm starting with, I always like to identify that as my given. So for example, I will write my 45.6 millimeters. I will set up my train track or my fraction. Do it like this. And one big thing that's really helpful is when you're setting up your fraction, you always want to make sure that you're diagonally cross-canceling your given units. In this case, because I'm dealing with millimeters in the beginning, I know that I need to have millimeters in the bottom. Whatever my target is going to go into the top corner. So in this case, my target is meters. Now looking at my king, Henry doesn't usually drink chocolate milk. I need to figure out which of my units is bigger or closest to the king. So looking at what is closest to the king, I have meters and I have millimeters. Because meters is closest to the king, I am going to denote this with a 1. So now I need to set up my fraction. For every 1 meter, I have 3 jumps between millimeters to meters. So each of these jumps represents a 0, meaning that for every 1 meter, I have 1,000 millimeters. Now to always check yourself, you want to make sure your millimeters cross cancel. Because they do, to solve, I would take 45.6 divided by 1,000. This will give me my final answer of 0.0456 meters. And that is my final answer. So now that we have done one together, try this one on your own and answer the question on the EdPuzzle. In just a minute, I will walk through it with you. Okay, so in this case, I have how many kilograms are in 5,603 milligrams. So I need to start off by writing down my given. So my given is 5,603 milligrams. I'll set up my train track. I want to cross cancel out my milligrams. So to do this, I need to make sure I put that in the lower corner. And my target in this case is kilograms, so that will go to the top. Now I need to figure out which one gets my 1 before I set up my fraction. In this case, the one that is closest to the king or farther to the left is kilograms because it is in that position. So that will get a 1, whereas my milligrams is all the way at the back. So I need to figure out, well, how many for every 1 kilogram, how many milligrams do I have? In this case, I have 1, 2, 3, 4, 5, 6. So I will have 6 zeros, meaning that for every 1 kilogram, there are 1,000,000 milligrams. So I make sure that my milligrams cross cancel, to which they do. And to solve, I am going to take 5,603 divided by 1,000,000. In this case, I get 0.005603 kilograms. And that is my final answer. Now that we have gone over scientific notation, the sliding decimal method, along with the factor conversion method, I would like you to try the basic skills inventory worksheet on Canvas. Now, this one will not be for a grade. However, if you are struggling with at any point in it, make sure you find that time to come see me because these skills are extremely important for your success in chemistry. If you are struggling with this video, you do have you have 3 total attempts, so you have 2 more after this. You may redo that to get the full credit from the questions. But again, if you're struggling with this, make sure you find that time to see me.